Hello and welcome. This task is about asymptotic notations, basically analyzing algorithms. To better understand what we are going to review in this task, it's good to know what asymptotic notations are and the different kinds of asymptotic notations. To have a rough idea, just by typing what are asymptotic notations in Google, we can see that asymptotic notations provides with a mechanism to calculate and represent time and space complexity for any algorithm. It is of three types: theta, big O, and big omega. What does this actually mean? Asymptotic notations provides with a mechanism, a way, a means to calculate, to estimate, and to represent time and space complexity. And one aim is to break down these terms into layman terms so as every listener can appreciate what we are trying to achieve. Time and space complexity has to do with computing entities, data structures. There is a constraint on time and there's a constraint on space when it comes to algorithms. There are three types of these asymptotic notations. We have the theta, the big theta, the big O, and the big omega. Big O notation is a mathematical notation, like a symbol, that describes the limiting behavior of a function. Limiting behavior of a function. What does this actually mean? Like if you see, let's use this for instance. This looks like a pretty good example. This is a polynomial. This is some sort of graph. Big O notation is a mathematical notation, which we talked about as being a symbol, mathematical symbol that describes the limiting behavior. What do they mean by limiting behavior? There is a limit at the growth rate for this polynomial. And we all know the x and y coordinates serve as means to measure or estimate the growth rate of a polynomial. So it's a mathematical unit that describes the limiting behavior of a function when the argument tends towards a particular value or infinity, as this polynomial tends to grow to infinity, as the value, as it tends to grow towards infinity. There is a limit in the x value, primarily the x. There is a limit, there are ranges at which it can get to, stay beneath, or exceed. If we use this chart right here, let's assume that this is the function or the polynomial we are interested in to check its rate of growth. It will not be easy for us to estimate exactly its rate of growth, but we can set boundaries for we can assume this to be its upper bound and this to be its lower bound. That means it will not get to this point, and it will not get to this point. It's only going to function between this upper bound and the lower bound. So in asymptotic notations, this will be considered big O, and this will be considered this big omega. Both of them, if we have a tight bound where we can say the polynomial will never get to this point and will never get to this point, we'll have those 2 points. We say that is a tight bound. We say that is big theta. Okay. I hope that gives a little bit of an idea. Now, big O is the upper bound asymptotic notation known as big O. Big theta is the asymptotic notation. Big omega, sorry, as big omega. This is the tight bound asymptotic notation, big theta. Definition of big omega, because this task is focused on big omega. What we have here is f of n is a subset of omega g of n such that there exists positive constants c and n0, that is c and n0 is greater than 0. Some texts have this as there exists c and n greater than 0. Some texts say states it at positive constant c and n0. It means the same thing. Where f of n is greater than a constant c times g of n for all n greater than or equal to 0. Now this looks a little bit complicated and funny, but it's plain English. Let's imagine we have a graph here. Okay, like we talked about, you have your polynomial here. Okay, this is y and this is x. Okay, now this, you are at this point right now. Let's call this 10, just a random value. And this polynomial was gotten from the analysis of a code written. Maybe before the end of this video, I plan to do a video to analyze two different algorithms, right from the steps down to the order, using asymptotic notation. I hope I get to do that. Okay, so you are trying to forecast, might be the word, to predict the growth rate of this algorithm. What is the essence? So as you can compare this algorithm, you can compare algorithms using the worst case, which is the upper bound, using the worst case scenario. Okay, worst case. It's difficult writing with the mouse. Worst case. Okay, so how this will be, you will simplify, first of all you will simplify this polynomial so as you get a simpler function that has this very similar growth rate as this polynomial. Okay, so you might end up having something like this, a simplified polynomial. And from the look of this graph, you can see that this polynomial f of n, mind you, we're using n because these are real integers. These are integers, sorry, these are integers, not real numbers. These are integers. We don't have decimal. We're not dealing with decimal points here. We're dealing with whole numbers, so we use n. If we are using real numbers, we use x. Okay, but we're dealing with integers, so we're using n. So our graph is not going to be in curves, but to be in points, because they are integers. That's by the way. So from the look of this graph, you see that this polynomial f of n will never get to this point. Okay, it will never get to this point. So we can say this polynomial is of the order g of n, big omega, big O, g of n. At the point, let's assume that there's a point here before the x-axis. At the point here, n0, this is n0 here, and this is c. Okay, c on the y-axis, n0 on the x-axis. Okay, so there exists this function, this polynomial is of the order big O of g o n, the simplified function from this, at the point c1 n0 equals, let's assume this is 1 also, okay, n0 equals 1. So this forms this definition. F of n is in the order big omega g of n, like we explained, such that there exists positive constant c n0 where f of n, which is this, is greater than c of n times g of n for all n from here and above, for all n0, for all n greater than or equals to n0. So from here and above, this graph will never come in contact with this again. But from n0 beneath, it's not applicable. It only applies above. So how, if you want to compare two algorithms, what is the upper bound, okay, of the, for example, a very simple one is a looping algorithm and a linear algorithm have different upper bounds. A looping algorithm has the exponential, is of the exponential order, while a linear algorithm of the exponential order of the order n. Okay, I think this is pretty this forms the summary or the background for this task. Okay, task 1. Let's prove that 8n squared log n plus 5n squared plus n is of the order big theta n squared log n. Okay, so how do we prove this? There are different ways you can prove this polynomial. In computer science, you can prove by induction if it's applicable to a constant k plus 1, if it's applicable to a constant k and also applicable to the same constant plus 1, then it's applicable for all cases. That it's, in a nutshell, that is to prove by induction. It can also be proven graphically. Okay, let's see the solution. F of n is equals to 8 n squared log n plus 5n squared plus n. G of n, this is the primary factor of this polynomial. This is the largest. This is bigger than this, and we'll prove that. F of n is equals to 8n squared log n plus 5n squared plus n. G of n equals to Gn is a simplification of f of n that still shows same magnitude of growth as f of n. According to the definition of big omega of n, which is this, f of n is greater than or equals to c1 times g of n for all n greater than or equal to n0 if we find such relationships, if there exists any of such relationship for any value of n that makes this condition, then this equation is true. So let's check. The coefficient of n squared log n is 8. Therefore, any coefficient less than 8 will be suitable, because 7n squared log n will always be less than 8n squared log n. Okay, so we have seen a value for C1, 7. This can be proven both graphically and by inspection. To demonstrate this graphically, using c equals 7 and plotting the graph f of n and g of n with various values of n to identify n0, consider the table below. When n was equals to 1, you put n here, 1 squared, 8 log 1, 0 cancels out, 5 times 1 squared, 1 plus 1, 6, is greater than equal to 0. Log 1 is 0. So everything boils down to 0. So when n is 1, 6 is greater than or equal to 0. When n is 2, that means this is 2. For those that don't understand, when n is 2, that means it's 8, 2 squared log 2 plus 5, 2 squared plus 2. Okay, that's when n is 2. You should get 54, which is greater than or equal to 28. So right from n equals 1, it's holding. Right from n equals 1, f of n is greater than or equals to g of n. Okay, that means n1 can be our n0. So we'll say n0 is equals to n1. Okay, and c is equals to 7. This is pretty easy. Now this is a chart. Remember I told you we're using points because of the n. These are integers. So right from here, you can see f of n is always greater than this. That means this will forever be the lower bound, and this will keep just like that. So now we can say this function will never be lower than this function. This is like the lower bound of this one. Pretty straightforward. Okay, so we can see here this confirms that from 0 equals n, 0 equals 1, this is in the order of this. Look again. 2. Let's prove that ax squared plus bx plus c is in the order of big omega n squared. We're using x now. Real values. No longer n. So this will be a curve. Okay. Still that. This will be a curve. This is lower bound. Remember, omega is lower bound. So this is f of n. F of x rather. F of x, and this is cg of x. Okay, cg of x, because omega is for lower bound. Okay, this can be proven by substitution, induction, natural substitution. Substitution is to substitute values, assume values, substitute and confirm the conditions. And okay, f of x is equals to ax squared plus bx plus c. G of x, this is the most significant contributor for growth. So g of x is equals to x squared. Let's assume. Now, a is equals to 1, b is equals to 2, 6 equals to 3. The equation is now x squared plus 2x plus 3. According to the definition of big omega of x, f of x is greater than or equal to g of x where there exist positive constants n0 and c. X squared plus 2x plus 3 is greater than or equal to c times x squared. Okay, so we're going to check if there exists any of such conditions. If there exists any of such conditions, then this is true. If we make c subject to formula, it yields x squared divided by x squared, 2x divided by x, 3 divided by x squared, which yields this. This holds true for x equals to x0. Now you ask me, how from here did we arrive here? Let's first of all equate x equals to 1. Okay, we're going to have 1 plus 2 over 1, x equals to 1, remember, plus 3 over 1 squared is greater than or equal to c. What is this? 1 plus 2 is what? 3. Plus 3 is what? 6. Okay? 6 is greater than or equal to c, right? So for this to hold true, c has to be nothing more than 5. Okay? Therefore, this condition holds if x is equals to x0 is equals to 1 and c is less than 5. See? So c now is going to be equal to 5. So this is possible. Had it wasn't possible, this equation wouldn't have held. Okay? So it's possible for only when c is less than 5. So I'm thinking this is going to be something like this. If you have 5, you have 10. If this is 5 and this is 10, it's going to be somewhere here. This is g, this is your lower bound. This is the g of x. And this is the f of x. This is your primary function. Okay? This point is x0 equals 1. This is c less than 5. Equals to 5, sorry. Less than 6. Hope this makes some sense. Why is this important to engineers particularly? We don't just write codes. Everybody, most developers can write codes. You can just write up a program, write an inefficient script. It runs, but it's not efficient. So with such knowledge, we can write very good codes. You check your code and ensure you're avoiding everything that is being looped, or you're managing it, but not like looping is terrible, but if you can avoid any other in exponential form except the inputs are very few. Okay, that's the reason why we analyze algorithms. So this holds true. 3. Prove that x again, this is not n, so these are real values. Just like we did in the first one, you simplify the polynomial, but that shows the same growth. You test the condition from the definition of big omega. Okay, since the primary coefficient, the coefficient of the biggest term is 12. If we reduce it to 11, it will always be lesser than this. We're looking at the lower bound. Okay, so we've gotten c. Then we test the values of x to see at what point this will always be lower. That means at what point f of x will always be greater than g of x. Okay, g of x. First of all, we reduce the coefficient of the largest term. Now we've ensured that c will always be lower than this polynomial g of x. Okay, the c that you multiply with the g of x, which is this, you got it from the coefficient of the largest term, will always be lower than this. Then you test all values of x to see if this will always be greater than this. Okay, That's exactly everything written here. So from 1, we see that 29 is always greater than 11. 2 is always, this is easy. Then you have the curve. Again, this is the lower bound of this problem. See, this confirms that n0 is equals to 12x 4 plus 9, 3, x raised to the power 3. This should be edited. These are superscripts. Okay, 3 rather. Okay, so we've come to the end of this video. Any questions you can post, any contributions. The essence of this is for us to share knowledge, okay, and to remember what we've learned at one point, because over time you need to at least look at what you've done and remind yourself. I hope this helps somebody as well as help me too, to understand better what I'm doing. Okay, thank you, bye.